All right. Next up, we have Jason Preston talking about wherever you go, there you are, the case for Panspermia.
Guys, forgive me a moment. I am so nervous that I forgot to get my handy printout. Here we go. All right, let's kick it off. All right, so there's a punchline to this talk. When we get to the end, you'll see why I'm calling it what I'm calling it. Wherever you go, there you are. Slide 1 here. There's not a lot of text for you. I hope you're an auditory learner because I didn't put any text up there. As research into the origins of life accumulates, we continue to build out a more complicated view of what the very first life on Earth was. The conservative estimate is it started 3.8 billion years ago. You can stretch that back to 4.7 billion years. But however you slice it, they basically don't leave much time between water not boiling off and the simplest chemicals being able to hold intact and us seeing fully formed, organic, presumably DNA-based life in multiple different substrates that imply instant adaptation to multiple environments. So at the same time, at the same outset, we see at least 3 different types of life in 3 different types of rock or hydrothermal situations. And so at the instant it starts, it's a fully formed cell. It's already worked out how to reproduce, maintain uniform cell size, and metabolize a lot of different materials. That presumes internal genetic complexity of at least several thousand genes. So we're not talking, we can't have like an originator life form start off at the start of life with, say, the minimal genetic diversity from an RNA precursor, and then have this incredible ability to adapt to all these different chemical environments with much less. But it also mentions some other reasons why I'm laying out that the first life we see on Earth, we probably need to estimate that it had thousands of genes at the point we see it in the fossil record. So here's a little chart of like the microbes on Earth, and you can see that at the origin, you're already seeing like a tripartite diversion at the very earliest moment. And that's kind of what I just spoke to. Right at the beginning in the rocks, we see at least 3 different kinds showing up. This is remarkable for several reasons. So one is, it takes time for genetic complexity to build up. And some of the most bizarrely intelligent research I've seen on this comes from a guy named Sharov. And I can provide the links in the documentation online we put up after the conference. But he and a partner worked out mathematically how long it takes for different types of life to build up genetic complexity over time. He looked at mammalia, reptiles, fish, all the way back to fungi and bacteria. And he basically eliminated any redundant genetic code and any non-coding genetic code. And he said that the functional, non-redundant genetic complexity builds up at a rate of 7.8-fold every billion years. So when you count back from all the different clades of life on Earth, you get back to the point of 3.8 billion years ago, and you're looking at life that is at thousands of genes, which is what would make sense for the diversity we see at the instant it starts on Earth. And that's all just DNA evolution. The strongest hypothesis as to where DNA came from is that it was from an RNA-centric life form. RNA it's a jack of all trades, not too good at anything. And so we know that that's kind of what where DNA came from. That's not all. DNA and RNA have been assessed in comparison to thousands of potential alternative genetic codes. Here we have a dot for each of those alternative genetic codes. And you can see that there are about 1,153 of alternatives to DNA. They're assessed here on how well they avoid error copying, and also another fitness factor of their ability to carry out parallel codes without failing. And to the top right, that's the best possible genetic language. DNA is right there. So if DNA just was happened upon by life, just randomly, Monte Carlo, from all these possible alternatives chemically, we wouldn't see that. It's infinitesimally unlikely. What much more likely is that this means that all of these alternatives reacted together in a common environment and had their own selection process applied to them. Like that is one of the most, and I'm asking you to take, follow me when I say take a lot of liberties. This is panspermia, it's very speculative. I'm going to play fast and loose with the truth, but the truth is going to like it. So, yeah, this to me implies that if this is the start of where we see life, this is the background, that alternatives were tried, and this one won out. It won out so hard, we've never seen anything on Earth that isn't DNA or RNA. We had to make these alternatives in the lab, although they're equally chemically plausible. So that also implies a period of time before 3.8 billion years ago, when you see this guy show up with 5,000 DNA genes. So how much time are we talking? From the start of competition between genetic languages to the appearance of life on Earth? Plenty. Back to this. This was this mathematical estimation of non-redundant functional genetic complexity across different clades of life on Earth, and basically assuming that these guys topped out here, these guys proceeded on to build up more complexity, and so on. This is the formation of life on Earth. This is 4.5 billion years ago. Water boils before this point. Life can't be on before this point. But presumably, life did not just instantly appear with 5,000 genes or, 100,000 codons. This trajectory is logarithmically linear, all the way back to 9.5 billion years ago. Does that make sense cosmologically? I think it absolutely does. What was happening back then? There was no Earth before up here, each of these lines being a billion years. There were plenty of stars. There were population 3D stars at the beginning. As they died, they left a residue of what astronomers call metals. We call everything but helium and hydrogen. As soon as you have that mix, after population 3 dies, right around here, you start to have enough material to build these genetic languages. That leaves a lot said about whether they would start forming right away, but you have a big playground to work with. It's vastly denser than our modern universe. So you have dense nebula and very weird radioactive environments where this can happen. It's the perfect chemical lab. And this process could have started as early as 500 million years after the Big Bang. So, let's look at this timeline that I'm asking you to consider. Big Bang, 13.5 billion years ago. Heavier elements accrue as the first generation of stars die. Soon after, genetic codes start competing. In interstellar space, RNA-centric life starts to win out. Then, sometime by 9 billion years ago, as in that projection line, DNA starts building up its complexity. It starts taking over RNA's job and saying, let me take that off your shoulders, I'll start building up a record of the code we need. DNA is brilliant at it, and RNA says, sure, run with it. So DNA is first copying 50 genes from RNA, and then it starts building from there. And it has the exact right amount of time to follow that timetable. Every billion years, it gets 7.8 times as complex. And so, the whole time, it's presumably spreading, multiplying. When we get here, it hits Earth. And at that time, it would have thousands of genes. So what does it do when it hits Earth? It's got enough diversity to say, I've got several things on the menu I can eat. I immediately can survive a range of environments. And so it immediately starts diversifying and creating a biosphere. So, let's humor this timetable. Let's think about how did this happen? What are any indications that all of these biological materials, the amino acids and the nucleic acids that we're really talking about, can they form without planets? Can they form all the way back? Yeah. Glycine is one that astronomers have been looking for. They know that it's key to life. It's an amino acid proper. It's in all our bodies right as we speak. And they've multiple times in the last 15 years seen increasing signatures that it's out there in interstellar space, along with other branch chain carbon molecules. So we see the complexity happening in these stellar clouds. And that's nowadays when the stellar clouds are relatively cool and dispersed and less irradiated. Irradiation matters because these things can form left-handed or right-handed. all amino acids on Earth happen to be the left-handed form. They could easily form the mirror image. But life on Earth decided universally we're just left-handies. And as it multiplied, it made more and more left-handed copies, 0 right-handed copies, 0. We're talking chemistry, so there's always a little bit of mess. There's a meteorite that is called the Murchison meteorite. It was found to contain both amino acids on Earth as well as variations that aren't used in Earth life. So it wasn't coming from Earth. All of the amino acids that were in it had a preponderance of left-handed molecules. The justification for that is it implies a few things. These didn't come from Earth. This wasn't a meteorite that came from home and fell back. And while it was out there, it got hit by right-handed polarized ultraviolet radiation. That happens when certain supernovas go off. They can have polarized light, and that light can sometimes it has to adopt a left or right-handedness. So a supernova bathes a nebula gas cloud in this light. The right-handed ultraviolet light destroys everything but the left-handed molecules, but preferentially rips apart the right-handed ones, leaving a perfectly sorted out soup of left-handed molecules. So that's what we see on Earth. We actually don't have many alternative theories as to why we're all lefties. We basically think we needed to be somewhere where light was corkscrewing the right direction to break apart all these and leave these preferentially. And we need that to be somewhere that doesn't have an atmosphere to protect life from that radiation. It doesn't happen here because we've got this nice blanket above us. It doesn't happen deep inside of a rocky core. It has to happen somewhere with no atmosphere, either on the surface of a bald planet or in an interstellar cloud. That's where this kind of radiation happens. So that's some evidence that, indeed, these chemicals did start off-world, off any world. So space could make life's materials. Can life itself exist in space? Well, just in the last year, Canadian virologists discovered that at the very edge of our atmosphere, right where you're basically just about to fall into space and gravity's not about to stop you, 800 million viruses rain back down to Earth per day per square meter. You put out a fishing net this big, wait one day, you will have 800 million viruses caught in it at the end of one day. That's happening across the surface of the Earth, at least above the bioactive zones where the currents carry viruses that high, all the time. We know enough about fluid motion to say that not all of them are falling back. These are extremely lightweight objects. As oxygen drifts off into space, so do these viruses. Earth is constantly exhaling an incredibly unfathomably large amount of viral material made out of amino acids and nucleic acids. So we know this is happening now. We know. We ourselves are proof that space is full of these materials. And my friend tardigrade is proof that even animals made out of multiple cells can somehow, for some unknown reason, survive a trip to space. They freeze without shattering, they shrink up and freeze dry, and then when space, leaves and they're back in an atmosphere, they, warm up, they fill back up with liquid water, and they repair any damage that radiation did. Why do they do this? It's hard to imagine in context, but I might imply one at the end of this talk. So life can survive a little trip to space, right? Even animal life. But a long trip? How long are we expecting life to hop between planets without dying in the process? This is the Kepler Orrery 5 from 7 years ago. This is how many planets we knew about 7 years ago for sure in our local area. So this is about the density throughout our galaxy of planets. And you can see the blue ones roughly represent how many of them are friendly to liquid water. You can see that there are a lot of gas stations as these things travel throughout the universe. If they need to repair in an unsafe environment, repair genetic code, they have a lot of ways to do that. And we know that the average debris floats through space at tens or hundreds of thousands of miles per hour relative to the solar systems, the star systems. And so it really adds up to maybe a 10,000-year trip from one planet to the next. And with a profusion of viruses coming off of each planet of 800 million per square meter per day, and that a portion of that, it's pretty easy to imagine that maybe enough actually makes it. You know, the odds are against it, but life is constantly just playing the numbers. And if this was happening, you know, a long time ago, then it's fairly easy to see how this might have happened. Note that in my timetable, DNA had to win out and start its own journey, at least locally, against the other codes, after 4 billion years. And so, for the next 9 billion years, it's kind of at the run of the playground, at least locally. That implies something creepy, and I'm about to get to it. That implies that Mars, if you go there and find life, I would bet anything it's DNA life. Not a cousin of DNA, exactly DNA. Because Mars couldn't have started growing this life any earlier than Earth did. If we go to Alpha Centauri and find life, I would bet a modest amount of money it's DNA-based life, or was before it did something extra cool and different. We might be surrounded by our own family members. Everything made of DNA on Earth is a family tree. Every virus that's killing your uncle and every cancer cell in you and this virus is going into space, they're your family tree. We could actually draw out the tree. We could expand all of our little genealogies, and we could even do that from star to star, possibly throughout the galaxy. At least a swath of the galaxy might very much be a DNA family, a common lineage. The other crazy implication to me is just this. After all these considerations, when I see this happen on Mars every summer, I lose all my resistance to what most people already, in their heart of hearts, as chemists, have to admit to themselves, which is methane comes from biological waste. It comes from bacteria. And chemists say, we don't know a simpler way to make it, a more plausible way to make it. If it's not coming from microbes on Mars as they thaw out each summer under the rock, then it's doing something that we've yet to really figure out how it's plausible. And so Occam's razor, usually the enemy of crazy theories like mine, is its friend. And that is our family member waving at us. And we should go meet them. Do we have time for questions? Oh, I did it right. I wanted there to be lots of time for questions because I bombarded you. Yeah.
So how do you feel about the second law of thermodynamics and the soul being impossible real? Oh, I said that. So I'm wrong.
That's a great point. Yeah. I want to address that a little bit. That speaks to my heart. Evolution's a beautiful thing. We know it runs off of randomization. We know that it doesn't happen in simulation or reality without random feedback from usually radiation. And what strikes me as amazing is second law of thermodynamics is fine. But I also have a body of evidence called me. Everything I love about myself, about you guys, my girlfriend, my pet dog, and trees outside, and my biosphere, came from life evolving. And every one of those things came from a genetic mutation. And every one of those things came from the chaos and randomness of Monte Carlo style thermodynamics. And so, right. Occam's, I mean, we all need to worship Lord Occam, right? But at the same time, we really need to wrap our heads around the idea that the chaos in our universe that is inextricable to it. Try finding me a cubic meter of space that doesn't have radiation that can knock a genetic code out of whack. That it's our friend. We might all die of cancer, and yet, at the end of the day, the balance says everything we love about life, about ourselves, everything that grew from life, came from that process. That process is our universal benefactor. It might extract a cost that is gruesome, but the balance is everything we love came from it, and only some of the things we hate came from it. So I do find that personally very touching. Yes?
On Earth, from all of the soils and bacterial organisms that are living beneath the sea, beneath the Antarctic, deep underground,
Right.
Is there an analog of are they methane generators similar to what you're discussing as possible potential on Mars?
Yeah, I think that there are extremophiles that, live under soil or in an extreme environment, hiding from the atmosphere or hiding from radiation that do end up with methane. I can't name one offhand, but I've seen enough diversity in the extremophiles, and I also have seen that for animal microbes, that's such a common waste product and such a simple one. I mean, the methane molecule is so simple, it's almost bizarre that it can't come from another process as easily as from this complex factory of life. But nevertheless, that's the case, and yeah, it's something life just so consistently decides to do. You know, all of life's diapers are full of methane.
Do we know yet enough about the percentage of methane in the Martian atmosphere, or how it may have evolved, and how does that track methane in an Earth analog?
No, I don't think we do. I know that it fluxes by an order of magnitude almost between summer and winter. So it dissipates, in other words. It seems to us that whatever life is enduring on Mars and scraping by, it's not figured out some clever way to go after the methane and recover it the way that plants and animals worked out something on Earth. It doesn't seem like there's a feedback loop. It's just, it's a fart once a year. That's what it is.
You know, you mentioned the viruses. That was very interesting about at the extreme altitudes.
Yeah.
Has anybody done any research on their viability and how long they live?
Yeah, well, that's the beauty of a virus. I remember learning in biology class that they're simpler than a living cell, but we don't think that living cells came from them. We think they devolved from living cells. Yeah. And so it's almost like wherever the living cells go, then they kind of branch off these devolved, inanimate, crystalline, and much more durable structures that we call viruses. Because they tend to not be this aqueous bag of ocean water, that actually enhances their viability and makes it less likely that they're dysfunctional when they come back. They're much smaller and they exist in greater profusion. So it's like life is playing the odds and saying, I'm going to make a lot of very dense copies of nucleic sequences, and basically space is going to rip them apart. But there could be a million of them in the space that a large bacterium would take up. So we basically are just trying to maximize the number of copies, and that means that viability. How many viruses do you need to get back to Earth to be viable?
But you know, one of the things, as you were talking, I just thought of the fact that none of them were found in the lunar samples.
Huh.
That would kind of say
that
near a neighbor, and we haven't seen anything with all of the time that's been spent on the samples that were brought back. And say that didn't happen.
Right. So my mind goes immediately to, my form of debate is I typically accept the point and try to immediately maneuver around it. I think that one of the viable options is that life typically tends to do best when it hitches a ride on an ejecta from an atmospheric impact. And so that's another way that the life could be making it through space. It's like a chunk of soil and rock goes up and a piece of life is right in the right spot inside that chunk to make it. The other option is the moon has 0 atmosphere, and so that's just too brutal a landing spot for it. And so every time it's landing there, it's just immediately getting ripped apart by a nice sun bath. And that's not a great answer. But it does imply to me maybe life is trying to hop to things that have atmospheres more than bald objects like the moon and asteroids.
But if it were doing that hop on a, let's say, inanimate rock, there still should be remnants on the moon, because if it's going to make it to the next star system, but the moon is a much more benign environment. The last going, 43 light years.
That's the potency of your point. I also would argue, though, that I'm not sure that they didn't find any materials, because every time they've looked at any object that came back from space, they find like some organic material, and they always manage to trace it back to Earth. So they're always saying, okay, well, we actually identified that was contaminant. And so anything that came from Earth would have been written off as contaminant.
You always find what you're looking for.
You're
looking in the right place.
So I do think that might have been an element. Yes?
Question, given a couple minutes late, so I might have missed this. Your timeline for genetic diversity was based on a linear logarithm as opposed to any sort of parabolic.
Yes.
I was curious about what the basis for that was.
So these guys were mathematicians by trade and also biologists. So they did this double they basically were in a unique position to do this calculation, and a lot of biologists haven't really been able to rebut it because they don't have that math background. So what they did was they basically said that we need to account for possible different speeds of complexification, right? Evolution is nothing if not creative, and that means speeding up and slowing down a lot of processes. So they were actually struck by how linear the relationship was when they tried to break that theory by incorporating such a wide range of Earth life. So that, when they brought in like cyanobacteria and animal bacteria, and then slightly more complex things like algae and on up to mammals, they were basically trying to break that linear relationship and see if there was something more complicated, because it's suspiciously simple, But it also means that the evolutionary tree that we all agree on, where the bacteria existed here, but then algae appeared here and mammals here, it also jived with that basic knowledge of when each thing emerged, through all of the biological clocks we use to estimate the family tree of life on Earth. So from a lot of different directions, that line is locked in fairly well for all the data we have, and we really tried to get, confounding variables in there, or data that didn't agree with the line. But no one's yet been able to come up with a single data point that goes off that line even a bit to imply that we need to do a different curve fit, And so, there's some logic to the idea that genetic processes are so random and such a rampant, chaos that they do wash out a lot of those local differences in technique when you look at the big picture. They do end up going back to a very simple logarithmic scale in some of the ways that they develop, just because of the washing out of more complex things that happen locally. Yeah. You want 3 minutes left? Okay. I want to,
Just real quick, a lot of processes that are split between being geologic versus biologically produced when you have chemical analysis. There's isotopic differences that show up. Is there anything that has to do with methane between a geologic and a biologic that would generate a difference in methane?
I don't know, and that's a really good question, because I haven't read anything about any look at the different isotopes that might have been involved in the methane, in the component carbon or anything. Yeah.
The classic biological story of life on Earth is you have this primordial soup sloshing around for
right.
Billions of years, and then suddenly the first cell was formed, complete with RNA, DNA, and all these enzyme systems. When is that going to start being replaced with a story, an equally fanciful story that someplace in a galaxy far, far away, a long time ago,
yes,
life began with primordial soup sloshing around in some ocean bed?
When they realized that the soup was boiling, right before all of those complex things appeared.
Somebody left the burner on?
Yeah, there was no time. There was no cook time. And that to me is the most compelling image. Is that, those earliest traces we found, they disagree on what time they represent, but they agree that it represents a time where the oceans were right at the edge of boiling. Those first life forms they found in the hydrothermal vents. The tardigrade thing?
Yeah, I was going to ask.
Yeah. So I think.
How did that evolve?
I actually think that if there was ever an extraterrestrial on Earth, it's that.
Yeah.
And it seems extremely impossible until you realize that, there's actually a case to be made that the extraterrestrial life is DNA. And so, of course, you wouldn't recognize it as an alien. You just wouldn't, especially if it's been doing little commutes back and forth. It seems like it's quite the commuter species. If anything on Earth that is multicellular has been evolved partly to survive space, it's that guy. Yeah. Well, it actually makes me be able to watch that again, because now I can say, sure, it's plausible that they're all humanoid.
But it shouldn't have evolved, should it? That ability. There's no...
Right.
There is no reason to evolve the ability to...
There's nothing like a vacuum. There's nowhere on Earth that's 1% or less of 1 atmosphere pressure that we know of. That we don't think there's anything that's just living up in the ionosphere, let alone an animal. Imagine how hard it would be to date, to raise a kid up there. So I don't know. I do think we might be looking at an alien. And it's not so disappointing when you realize just how alien DNA life is on Earth. we're still going to find some truly exotic and fun weirdos out there. Yeah.